All right, so now let's go ahead and start working with some data. Let's actually get a map going, because we're doing spatial data analysis. We need to be doing maps. So what we're going to do is I'm going to read some data in. I'm using read.table to read in the Scotland.dat data sets, skipping one line. And then I'm going to specify the names of the data frame. To be district, observed, expected, PCF, latitude, longitude. Now this code won't run for me. Tried, wouldn't work. Now let's pull in some spatial data. So now I'm going to pull in a spatial polygons data frame using rgdol read OGR. I'm only going to get the Scotland layer. And here I'm allowing loss, that if there's something to be lost, there's a problem, just go with it and proceed forward. Now you'll notice that when I look at that spatial polygons data frame, it does not have a projection yet. So using this function, I'm like, hey, what's my projection on this? Oh, I don't have one. I need to deal with that. So what I'm going to do here is I'm going to specify that the projection is going to be the WGS84 projection. That's a good default projection. And I'm using the CRS function. All right, so now let's just take a look at what we've got. Let's check out our data. So here, how the author chose to do this was to grab the individual slots of the object of the spatial polygons data frame and just look at their class. So here, when I look at the data, we can see that we have a name and we have an ID for each row of our data frame. Okay, and so here are our IDs. Now, something that's going on is that we have two things, two objects for Scotland. We have a data frame, and then we have a spatial polygons data frame. I'm going to need to match them up. Well, fortunately, the IDs are in here. In the spatial polygons data frame, we have an ID column for the ID variable, while in the Scotland data frame, it's recorded as district. So what we just need to do, we just need to match up the district with the ID. Boom, easy peasy, lemon squeezy. And here I'm setting up, I'm organizing my data frame. Making sure that the row names match. So remember, when I work with a spatial polygons data frame, I need to make sure my row names are in a consistent order. Or otherwise, I'm just going to be doing spaghetti matching, and that's not going to work out. And now we have a spatial C-bind going on, where I'm doing a C-bind on spatial polygons data frame and on the regular data frame. It is absolutely critical that I have my rows in the same order. And you'll notice that I changed the order on the data frame, but I left the spatial polygon data frame alone. That is good practice. You really don't want to mess with this one, because the rows of this object are connected to your spatial polygon, spatial lines, stuff like that. Here, these are just individual rows of data. Shuffling around isn't going to change anything about the data. All right, and so now we're just double checking, is everything good? Is everything all equal? So that if I got a false, that would mean one or more rows didn't match up correctly. And so now I've got all my data, I've got all of my Scotland data inside my spatial polygons data frame. So now let's actually start mapping some stuff out. Okay, so what we're going to do is I'm going to take a probability mapping for the rates. All right, so I'm going to take observed and expected values, and I want to do some mapping. Now, what we're going to do here is we're going to compute relative risk. I'm going to use our observed data and our expected data. So now remember, anytime I'm working on a project like this, when we have situations like low population density, let's say like in Wyoming, then one observation, which may have been a fluke, could proportionately be very large, or an omission just by fluke may make things look like it's extremely low, when in reality it's not that extreme. And so we're going to deal with that in a moment, but first we're going to just do the raw modeling. I'm going to get the relative risk, and I'm dividing by 100 to make it a little bit easier. Something I can also do, okay, so for here, we're taking crude rates, expected counts of cases, relative risks, and Poisson probabilities, but we're just going to, so that all of this gets computed by the prob map function, but we're just going to look at relative risk for the moment. We're not going to worry about the rest. Now, anytime that I'm dealing with a situation where we have small population size that we're sampling from, one observation up or down can change the interpretation by surprising a lot. So what we're going to do to make things a little bit smoother, a little bit easier or a little bit more reliable, is I'm going to pull in some outside knowledge. I'm going to pull in some Bayesian information. I'm going to pull in Bayesian smoothing, and I'm going to go ahead and use some theoretical, what I believe theoretically to be correct mathematically what's happening. I'm going to include that with my data so that I have something that is less sensitive to fluctuating values in small population areas. And so to do that, I'm going to use the decluster package, EMP Bayes Smooth, and I put in observed and expected. And here is the smooth relative risk. Now I'm going to specify my projection. And now I'm going to actually go through and plot it. Now, what I'm going to do, I'm going to color code things to match up with what's going on, so it's easier for me to see what's happening. So here is my spatial polygons data frame that I'm, with the projection defined. I want to plot relative risk and smooth relative risk. I'm going to chop up the color bins by these values, and I'm going to define the colors using our color brewer palette, red and blue. I'm breaking it up into 8 different colors, and I'm reversing the colors just to make sure that things match the way I want them to. And so here we can see where the relative risk is greater or less. And we can see that we have, when I don't have the smoothing, we have more extreme values appearing on our map. Here we have less extreme things popping up. So here we can see that this is darker than over here. This is darker than over here. And I'm going to go ahead and save my spatial polygons data frame. Now, when I did this, you notice I saved one file or one object, but if I take a look at what was actually saved afterwards, you can see that I have 4 files getting in there. I have a DBF, a PRJ, a shapefile, and an SHX file. All right, so now let's go ahead and load some fires data. Now, the author originally got the data from GeoHub here and here. Now, I couldn't get this to run on my machine, so I just went ahead and used the author's file to be able to load this. And he calls it GeoHub R data, and you can get this data from the author's website. And so here we can see, here are the layers that we have: fire news, fires 30 days, fire 7 days, fires all, hotspots 1 day, hotspots 7 days, hotspots all. All right, so now let's go ahead and read in the shake file for the fires. And here we can see what the names are of our slots. Now here, this is just specifying some coordinates for a bounding box. So here I have the coordinates of my bounding box. Not really a bounding box because it's not a box, but I'm going to define it to be a polygon. And I'm going to pass that polygon into the polygons function. And then I pass that into the spatials polygon function to define where I want to plot all my fires. So everything will be within this shape. Now, what I want to do is I want to plot a map so if I was to take this here, what I've got so far and just start plotting, what would happen is I'd have dots, but I would have no reference of where they are on the Earth. So I don't know what's going on. So underneath my individual dots, I want to have a map that I will recognize, which we'll take the simple world from map tools. And I need to make sure that I have a consistent projection. Remember, that's always important. So I'm going to invert the fires bounding box to have the same projection as the simple world. And now what I'm going to do, I'm only going to look at the region of simple world that's contained inside my bounding box. I don't want the entire Earth. I only want the area that I have data. I only have data for. So what I'm doing is I'm taking the intersection in ArcGeo's package, take the intersection between my bounding box and the map that I want to put my data on top of. And now here are going to be some of the parameters for plotting. And you'll notice I've got that intersection I created a moment ago. Here's the line width. Here's the color of what the lines will be. And I'm specifying that these are spatial lines. Order matters on this also for how I'm going to use it in a moment. All right, so I'm going to take my data and I'm convert it to spatial temporal data. So here we've got fires occurring over time. And what I want to do, I want to set it up so that my fires are, I've got a location and a date. So I want to treat it as, time and space. So I take the dates and I convert it to the format. So here it's stored in day, month, year. But in data science, we like year, month, day, because that order, the dictionary order corresponds to actual date order. Now I'm going to look at the coordinates where the only where the latitude is north of the equator. I'm going to go ahead and sort the points by their date. And now here, what I'm doing is I'm taking the fires data points, and I'm saying, hey, these data points, the coordinates are spatial points, and I'm taking the data and putting that as the data frame. So there actually will be a little bit of redundancy in here because I'll have the coordinates twice, but that's okay. It's not going to cause a problem. And now to be able to put this into space-time, I'm going to need to convert this to a space-time interval object using the as function. And I'm going to say, I'm going to take that, I'm going to put it into the space-time plot function. I say I want 3 intervals. Here is the layout information, which I defined previously. And here is how large I want each fire to be, fire location on my map. Now, when I get this, you'll notice that I have blue dots throughout, and each of these 3 subplots, each faucet, has about the same number of plots. What's going on is that when I said that I wanted 3, it puts approximately 1/3 in the first, 1/3 in the second, 1/3 in the third. So you'll notice that time here, this is over a much longer time span than what's over here. and this is a much longer time span. So this is likely to be like summer, and this was the probably the preceding spring, and this was probably the preceding fall and winter. All right, so now let's say that I'm only interested in Greece. Okay, so what I'm going to do, I'm going to filter things out just like I do with any other data frame. I'm going to say that I want the country to be GR, which is, that abbreviation means Greece in this data set. And then I do everything exactly the same once I have that. Now, the code is a little bit more compact than how I presented it here. But ultimately, I get my 3 subplots. Now, something about this is that you'll notice that these islands suck. That this isn't a very informative map. Well, what's going on? If I look at Greece over here, and I'm far back, I'm zoomed out. There isn't really a whole lot of detail in there because I don't need it. I don't need the additional information in there. This is a very simple representation of the Earth. When I zoom in, I can see that there's more problems with that simplified map than there would be otherwise. And we can save what we've got going on using write OGR so that I can grab it later and use it. And if after I save it, so write OGR saves it, read OGR reads the file after I was done. And you notice that I'm specifying the data source name, I'm specifying the layer, the driver, dataset options, overwrite equals true, and to delete the data source name is true. And so I can read in what I have, and here this is just a little slice of it, just so that I can just see what's going on without having to load the whole thing going. Something else I can do is I can get the info about a shape. This is the same order that the author put in. I would put this with Scotland, honestly, but if I grab a shape file, I can use getinfo.shape from map tools just to see, like, what do I have, number of shapes, number of polygons, stuff like that. All right, so now let's take a look at reading a .tiff file. And I'm using rgdal once again, using read rgdal. I've got a summary function just to give me an idea of what it is I have. So here we can see our bounding box. We've got longitude and latitude. Here is our cell center and offset, cell size and cell dimensions. So this looks like this is a grid. Yep. Spatial grid data frame. And here is our data for the data frame itself. Now here what we're doing is whenever band 1 is less than or equal to 0 or it's greater than 10,000, I'm just going to call it 0. So here I'm inserting or I'm replacing values less than 0 with an NA. And it looks like it doesn't actually do anything to the larger values. And when I was preparing for the video, I printed it out, took a look at what's going on. What it's just doing is whenever there's negative, it becomes NA, and that's all this code does. Now here, this is another way to get things going, to access things and work with it. Here we can see the size of our grid. Now, what I'm going to want to do when I map this out, I need to specify my colors, I need to specify my breaks. And so here I am, just kind of using like subject matter knowledge and knowledge of the data to find good breaks to be able to specify what the colors will be individually. I'm choosing the terrain colors. I'm choosing 11 of them.